All right, moving on to section 3.2. Section 3.2, the derivative is a function. So we're going to, motivated by the previous section, now define the derivative of a function as a function. In the previous section, we defined the derivative of a function f at a point x sub 0 and denoted it f prime of x sub 0. So what we're effectively going to do is replace the x sub 0 with a variable x and have the derivative as a function instead of just having it evaluated at specific points. And the technique of computation will be similar to what we had in section 3.1. We'll use limits to compute derivatives in this section. In the next section, we'll have some rules of differentiation, and that'll kind of streamline the computation. All those rules will be established using the limit definition we're about to state. And if we encounter a new function, we haven't differentiated log functions, inverse trig functions, we'll encounter a handful of new functions in Calculus 1. You want to differentiate them, you got to go back to this definition. So everything is based on the following in terms of derivatives. The derivative of function f of x with respect to variable x is the function f prime, whose value at x is f prime of x equals limit as h approaches 0, f of x plus h minus f of x divided by h, provided that limit exists. And function f is said to be differentiable at each value for which this limit exists. So same idea we had in the past. Now we've got variable x instead of a fixed number x of 0. Maybe we use c sometimes as well in some of this differentiation stuff. It's the limit of the difference quotient, and we would expect it, and it does reflect the slope of a tangent line as a function of x to the curve y equals f of x. We've got a handful of notation. There's history behind this. There's a number of ways to denote the derivative of f of x. F prime of x, as we just introduced. If we write y equals f of x, then we might write it as y prime. The prime notation is due to Newton. We might also write it as df dx or dy dx. Really, f and y are interchangeable in most of this, or d dx, square bracket f. The d dx stuff means take the derivative of the stuff in these square brackets. So d dx is take the derivative with respect to x of function f. This stuff with the d's actually oftentimes is more useful, and it's due to Leibniz. That's where this comes from. We'll really just mix it up on all of these. When it's most useful to use this, the D notation, sometimes called differential notation, then we'll use that. Here in the beginning, we'll probably just use a mixture of the prime notation and the differential notation. Okay, we got a definition. It's expressed in terms of limits. So if we want to take derivatives, all we got to do is evaluate limits, and you're pretty good at this stage at evaluating limits. So find the derivative, dv dt. Okay, I use v's and t's instead of f's and x's, but they're dummy variables. Where v is a function of t is of the form t minus 1 over t. Okay, we'll go to the definition. Definition of derivative says derivative is a limit as h approaches 0 of the function evaluated at t plus h, t being the independent variable this time, minus v of t divided by h. Same thing we had before we had f's and x's instead of v's and t's, but same format, same limit. Limit of this difference quotient. Okay, so let's see, what is v of t plus h? I'll go up here to v and replace the t with a t plus h. It occurs in two places. So we'll have t plus h minus 1 over t plus h. Whenever I substitute in for a variable like that, I'll usually put it in parentheses. It's just easier to pick out. From that, we'll subtract v of t. Okay, that's t minus 1 over t. Be careful with the parentheses not to lose a negative sign. The limit will work out just fine, unless you change it into something incorrect, and then all bets are off. But we'll work these limits by factoring, canceling, and substituting, as we so often do. Okay, let's take this division by h and write it as a 1 over h out front to kind of eliminate the compound fraction and just to make it fit on the slide more practically. So here's the divided by h part, and that leaves us with this other part. Let's see, we got a t here and a minus t over here. So we can cancel the t and the minus t. That'll leave us with the h. There's the h. That'll leave us with a minus 1 over t plus h. There's the minus 1 over t plus h. And when I distribute the negative sign, that'll leave us with a plus 1 over t. And here's the plus 1 over t. So this equals what we had previously. Let's add these two together by getting a common denominator. So common denominator will be t times t plus h. So we'll multiply the first one by t over t and the second one by t plus h over t plus h. Usual thing to get common denominators. Yielding the common denominator, we get a numerator of negative t in the first and a numerator of t plus h in the second. Now we can add those together because they have a common denominator. And hey, look at this. There's a negative t and a positive t. Add these two together. The negative t and t cancel to leave us just with an h in that numerator. And there's what we get with the h up front and the 1 over h way out front. Okay. Hey, I can factor an h out of this. Of course, that's the goal, is to factor and then cancel and then substitute. But we can factor an h out of this stuff in the parentheses. H times 1 plus 1 over t plus h. Can you cancel the h in the 1 over h? Yeah, as long as h is not 0. It isn't. We're taking a limit as h approaches 0. So I'm starting to go through these limits a little bit faster as we're learning more about them and leaving out some of the details in writing. Maybe verbally, I'll still give you loads of details for a while. You can cancel because h is not 0 because you're taking a limit. So we've canceled the h's. You're good to substitute in. Yeah, h equals 0. Substitute that in. There it is in parentheses. That leaves us with a 1 plus 1 over t squared. So there's the derivative. Why are you good at plugging in the h equals 0? How about this? This is a rational function in h, and the denominator's not 0. It's t squared. Of course, t can't be 0. That's not in the domain of the original function. But like I said, we'll maybe verbally describe or justify some of these steps and not write it out in all the detail that we've done in the past. So there's the derivative of v with respect to t. Straightforward. Take the definition and follow your nose. The limits will be factor, cancel, substitute. Here's the factoring right here when we pull the h out. Canceled to get to this step, and here's the substitution. Factor, cancel, substitute. Of course, that's easily said. Factoring's probably the trickiest part, to get it in the right form to factor out the appropriate thing. The appropriate thing will be an h, that denominator, in all these derivative limits. Let's look at a second one before we go back to the notes, just illustrating the ideas of what a derivative is. So here we have graphed in blue, the function y equals f of x, and graphed in red, the function y equals f prime of x. This is an image from the book. The book actually had these aligned vertically where the x coordinates were the same, but it won't fit on the slide very well. So let's set them side by side and make the observations about what's the function doing and how does that affect the derivative. Okay, at point A, looks like we got a horizontal tangent line, a tangent line with slope 0. Well, the derivative reflects the slope of a tangent line. So at this same x value, the derivative will be 0. They didn't label it quite so clearly, but here's that same x value, and the derivative, sure enough, at this point is 0. they've labeled these points A, B, C, D, E, and the corresponding points on the derivative with primes. So at point A, where we've got out some x value, some y value, and a tangent line that has slope 0, on the derivative, there'll be a corresponding point, same x value, y value will be 0, that is, a derivative will be 0 at this point A prime, because at this point A, the tangent line has slope 0. Here at point B, they tell us the tangent line has slope -1. Well, then the derivative will have value -1 at the point B prime. Like I said, they've taken that point and they've drawn a little arrow. If you'll look at the image from the book that links those two together, yeah, we got the same x values indicated by this little blue thin vertical arrow. Same x values. If the slope here is -1, the slope for the derivative, the value for the derivative will be -1. Here at point C, we've got a slope of -4/3. Then at the corresponding x value, it looks like it's 5. So give us a nice x value there. At x equals 5, the derivative then will take on the value -4/3. -4/3. Okay, so that's around here. So it looks about right for the graph. Onto point D. Looks like it's around 9 for the x value. We've got a slope of 0 for a tangent line. Then the derivative will take on the value 0 at the point D prime. At point E, they've drawn a little triangle here, and they're making a claim that rise over run is approximately 8/4. It's approximately 2, approximately, they say. So the value of the derivative at point E prime should be approximately 2. And that's all what's explained down here. So there's how the slopes of tangent lines of a curve determine the values of a derivative. To illustrate what a derivative is, it's the slope of tangent lines. We can go a little bit further than that, so get a little bit more mileage out of this. Look at this, the blue function, it's decreasing. It's going downhill when read from left to right, from point A to point D. It's going downhill. Yeah, and between A prime and D prime, notice the derivative is negative. Well, if the function's going downhill, then tangent lines will have negative slope. At point A, we've got a slope of 0. At point D, we've got a slope of 0. In fact, we could even use these values to indicate how steeply the original function is going downhill. Notice the derivative takes on its largest in magnitude value at C prime, telling you at point C over here, between A and D, that's where we'd expect to see the steepest decrease in function f. So it starts out with a horizontal tangent line, and it starts to go downhill, goes downhill at its steepest right here, continues to go downhill but less steeply, and that's reflected in the fact that the derivative got more and more negative, reached a most negative value, the largest negative value, if you like, largest magnitude, but negative. And then it turned around and went back to 0. Yeah, it started out with a tangent line of slope 0. It got really steep, and then it got less steep back until it had leveled off again, where the derivative is 0 at point D or D prime. Then the function changes to increasing. Well, then the derivative should change to positive because it's a rate of change. If the function's going uphill, the derivative should be positive. If the function's going downhill, then the derivative should be negative. Also, how big the derivative is reflects steepness. The biggest value of the derivative occurs over here at the right-hand side, around x equals 15. So the function should be at its steepest at a corresponding point, and it is, as reflected by the graph. So derivatives are slopes of tangent lines, the rates of change as far as that goes as well, and we'll see a relationship between the graph of a function and a derivative is given here. Now, ironically, we'll actually use derivatives sort of backwards from this. We'll figure out properties of derivative and actually use those to graph functions. Here we're illustrating how we can take the graph of a function and relate it to the derivative. In applications, we'll probably take properties of derivatives and go backwards and use that to graph functions. Back to the notes. and a comment that says basically what I just observed. From the graph of y equals f prime of x, graph of the derivative, we can see where the rate of change of f is positive, negative, or 0. Where the rate of change is positive, the function's increasing. Where the rate of change is negative, the function's decreasing. Where the derivative is 0, it had a horizontal tangent line. I expect that just mostly to happen at individual points. That need not be the case, but that'll be the main case we'll see is horizontal tangent lines at single points when the derivative is 0. The rough size of the growth rate of f at any value x can be determined. Yeah, the steepness can be determined from how big in magnitude the derivative is. If the derivative is big in magnitude and positive, like in that picture we just saw close to 15, then I expect the graph of f to be really steep and increasing. If we had a big but negative derivative, I'd expect the graph to be steep and going downhill, steep and decreasing. And it tells us where the rate of change itself is increasing or decreasing. And I can look at the derivative and determine if the derivative itself is increasing or decreasing. Let's save that one for later. This is talking about the rate of change of the derivative, which itself is a rate of change. So this is some reference to the rate of change of the rate of change. It reminds me of acceleration, and we'll see soon that applications involve velocities and accelerations. One of the first applications we'll see of derivatives. Let's look at 3 more examples. Okay, here's a function. K of x equals 1 over 2 plus x. Find the slope of the tangent line at the value x equals 2 and differentiate. Okay, derivative is, by the definition, limit as h approaches 0, k of x plus h minus k of x divided by h. All you have to do on these is follow your nose. Substitute in, factor, that'll be the algebraically tricky part. Cancel what? You'll cancel the h's. There'll be an h in the denominator, no problem there. There'll be an h in the numerator once you get the thing factored. And then substitute. Okay, so let's follow our nose. What does k do to x plus h? Wherever I see an x in the definition of the k of x function, I replace it with an x plus h. So we got 1 over 2 plus x. Substitute in x plus h, we'll get 1 over 2 plus x plus h. 1 over 2 plus x plus h, I put it in parentheses, as I'll do. Minus k of x, I'll just copy down the function over here. Okay, we got a compound fraction again, a fraction within a fraction. Let's take that division by h and write it as multiplication by 1 over h up front to fit it on the slide mostly, and also so I can manipulate what we've got up here. So here's the division by h. That leaves us with this minus that. Let's get a common denominator between this and that. That denominator will be the product of these two denominators. So we'll need to multiply the first by 2 plus x over itself. And we'll need to multiply the second one by 2 plus x plus h divided by itself. So we'll get 2 plus x over 2 plus x times 2 plus x plus h. Right? Think about canceling the 2 plus x's. That'll get you back up here. So it's correct. Over here, we've multiplied by 2 plus x plus h over itself. If I were to cancel those, we'd get back the 1 over 2 plus x. So we've done it correctly. We've got a common denominator. We can add these together. Then we'll have 2 plus x minus 2 plus x plus h. So we'll subtract off that entire quantity there minus this quantity. We'll have a 2 minus 2. We'll have an x minus x, and we'll have a negative h. We'll just be left with a negative h in the numerator. Now, if these steps are too fast for you, pause the video and check them for yourself. So I am skipping some of the really elementary algebra steps. It'd be a good idea, make sure you understand them, because these are the kind of questions you'll get on the test. And you'll have to do all the algebra steps to know what's going on. So skipping slight algebra steps simplifies down to this. So we got it factored, got an h in the numerator. We can cancel that h with the h in the denominator. We'll be left with a -1 in the numerator. Denominator has become this. Can you plug in h equals 0? Yep. It's a polynomial if you want your reasons why. And we end up with 2 plus x times 2 plus x. That is 2 plus x squared in the denominator. And we pick the -1 up in the numerator. So the derivative of 1 over 2 plus x is -1 over 2 plus x, quantity squared. They wanted the derivative, and they want to know the slope of a tangent line at x equals 2. Well, a slope of a tangent line is the derivative evaluated at that point. The derivative k prime evaluated at 2. So we plug in 2 for x. We get -1 over 2 plus. It's in parentheses because I substituted in. 4 squared is 16. We get -1 over 16. That tell you anything about the graph of this function at x equals 2? Slope of a tangent line is -1 over 16. It's negative, so the graph of the function is going downhill. It's a decreasing function at x equals 2 because this is negative. And 1/16 is a kind of small number. It's going downhill, but very shallowly because 1/16 is a small number. So I can tell that just by looking at the derivative. And we'll use derivatives to graph quite soon. Let's do another one. Okay, they introduce, I'm not sure it's introduced here or if it's introduced earlier. I think it's introduced in the homework here, possibly in the section. An alternative form for the derivative of a function. This we'll use occasionally, and I prefer my h approaching 0 stuff. But this will arise now and again. So let's do an example that illustrates it. The alternative formula for the derivative is f prime of x equals a limit as z approaches x of f of z minus f of x over z minus x. Rumor has it, that's the same thing we'd get out of the other formula. Notice the z is limited out, so there won't be z's when we evaluate the limit, just like there's not h's when we evaluate the limit in the regular definition. Use this formula to find the derivative of x squared minus 3x plus 4. Okay, so we'll just take the formula and substitute in and factor cancel substitute to evaluate the limit. F of z, okay, here's a function, so that'd be z squared minus 3z plus 4, there you go, minus f of x. I'll copy that down. Don't forget the parentheses. If you forget the parentheses, you won't be able to factor and you'll be stuck. Z minus x in the denominator. Some things cancel, as long as I kept up with the parentheses. Let's see, we got a z squared minus x squared. Okay, there's that part. We got a -3z plus 3x. Let's write that as -3z minus x. Same thing. -3z, and we got a plus 3x. When I distribute the negative sign, here we've got a plus 3x when I distribute the -3. And we got a 4 minus 4. So we can eliminate the 4 minus 4 as 0. So the numerator becomes this quantity here. I've bracketed these together because remember, we're trying to cancel. Cancel what? Well, this time you're trying to cancel the z minus x. Can you plug in z equals x? Of course not. You get division by 0, which is why you have to do some canceling somewhere. So I'm looking for z minus x's in the numerator. I found one. Hey, there's another one. Z squared minus x squared, that factors into z minus x times z plus x. We've got a z minus x common factor in the numerator. I can factor that out if you like, and then cancel. So I cancel the z minus x's in the numerator with the z minus x in the denominator. I skipped a step of algebra. Please make sure you're comfortable with that. But we cancel the z minus x factor in the numerator with the z minus x in the denominator, leaving us with this thing, z plus x, and this thing, minus 3. Z plus x minus 3. So we've canceled these two in the numerator. It's a factor with that z minus x factor in the denominator. Don't just cancel one of them for God's sakes, because that ain't how algebra works. Can you plug in z equals x? Yeah. Nothing goes wrong. We got a polynomial in z, to be technical about it, and would get, let z equal x, we'll get x plus x, put it in parentheses where I did the substitution. would be useful for you to adopt that habit as well. It's easier for you to check your work, and it's easier for somebody else to check your work. And so we get what? 2x minus 3. So this alternative form of the derivative gives us that the derivative of this function is 2x minus 3. You want to use the h stuff. It'll work out quite similarly if you take a limit as h approaches 0 and use our original definition. Match the given function with the derivative graphed in figures A through D. Okay, there's a pile of questions from this section 3.2, number 30, 28 through 31, or 4 different graphs they give you and tell you to match it up with these A through D things. Let's do the one corresponding to this function, f sub 4 of x, I guess. What's up with this? How about we look at, well, I'm thinking 2 things, where it has horizontal tangent lines and where it's increasing and decreasing. It's got horizontal tangent line here, here at the origin, and here. So the derivative should be 0 at the x value corresponding to this point at the origin, well, the x value 0, and the x value corresponding to this point. There should be 3 places where the derivative is 0. Derivative here is 0 in one place. Derivative here is 0 in one place. Ooh, this one's got a derivative that's 0 here, here, and here. 3 places. This one's got too many zeros. 1, 2, 3, 4, 5 places where the derivative is 0 here. It's got to be this one. So 3 horizontal tangent lines, 3 places where this graph is 0, where the y value, the y prime value is 0. All right, so it's got to be part C, problem C, graph C. We're just trying to learn stuff here. Let's look at where this function's increasing and decreasing and compare that to the positiveness and negativeness of this graph C. Okay, let's go ahead and expose all of this stuff. Let me put little arrows where this has horizontal tangents, and let me put little arrows correspondingly where the derivative is 0. Okay. From here to that first arrow, f sub 4 of x is decreasing. Read from left to right, it goes downhill. Okay, then the derivative should be negative. Decreasing function, negative rate of change, up to the little arrow. The 3 arrows represent the same 3 x values. So decreasing function, negative derivative. 0, horizontal tangent line, 0, derivative. Now the function goes uphill, it increases from here up to the origin, from here up to x equals 0. The function increases, so its derivative should be positive, and it is. Turns around, starts decreasing from here over to the 3rd arrow. From the 2nd arrow to the 3rd arrow, the derivative is negative. To the right of the rightmost arrow, the function's increasing. To the right of the rightmost arrow, the derivative is positive. So the derivative is positive and negative, where correspondingly the function is increasing and decreasing, respectively, if I said it correctly. This is positive here and here, and this function is increasing here and to the right in corresponding places. Where the derivative is negative, the function is decreasing. Where the derivative is 0, the function has horizontal tangent lines. And that's what derivatives tell you. It tells you where functions are increasing and decreasing, though we haven't formally defined that just yet. And it tells you where it has horizontal tangent lines. So definitely this red graph is a graph of the derivative of this blue function on the left. Okay, time to do this one, number 44. Yeah, let's save that one for one more definition. Function is differentiable on an open interval if the derivative, as we've defined it, is defined for all x in that open interval. Now, when we look at endpoints, look at closed intervals, say of the form a to b, then we want the usual behavior on the interior points. And like we did with continuity, we'll settle for some one-sided limit stuff at the endpoints. So we'll talk about the right-hand derivative at a, the left-hand endpoint of the interval. So x is defined to the right of a. So that's why I have to take a right-hand limit, a right-hand derivative. It's defined to be a limit as h approaches 0 from the right-hand side, the positive side, of f of a plus h minus f of a over h. Same kind of thing we had originally, except one-sided limits, because we're dealing with an endpoint of the domain. At point B, the right-hand endpoint of the interval, we'll have to take a limit from the left, from the negative side. And we take a limit as h approaches 0 from the negative side of f of b plus h minus f of b over h. So being differentiable on the closed interval means the usual thing inside that interval and some one-sided limit stuff, right-hand derivative and left-hand derivative at the endpoints. We could also use one-sided limits to check for differentiability if we had a complicated function, and that's what happens in number 44. They've given us a piecewise defined function. And they say determine if the piecewise defined function g is differentiable at the origin. How many functions do you see here? One, its name is g, but it's come and defined in two pieces. When x is negative, it's this piece. When x is greater than or equal to 0, non-negative, it's this piece. Just determine a differentiable function. Well, let's see. G is piecewise defined, as we had to do with piecewise defined functions. Let's consider one-sided limits. The terminology here is left and right-hand derivatives at 0. Okay, so let's take a limit as h approaches 0 from the positive side of g of 0 plus h minus g of 0 over h. That'd be the right-hand derivative at h. Even though it's not an endpoint of the domain, we'll still have to check one-sided limits because the function's defined piecewise. Which piece do you use? Well, that depends what you put into the function. When you put 0 in, which piece do you use? X equals 0, you use this piece. When you put 0 plus h in, which piece do you use? Is 0 plus h negative or non-negative? Oh, good thing we're taking a one-sided limit. This is why you have to take a one-sided limit. H approaches 0 from the positive side, so h is a little positive number. So 0 plus h is a little positive number. Which piece do you use when you input something positive? This piece. So g of 0 plus h, since 0 plus h is positive, is 2 times 0 plus h minus 0 plus h cubed minus 1. Exactly this. Put parentheses around it just to be careful. Subtract g of 0. At 0, we also use this piece. Plug in 0, we get 2 times 0 minus 0 cubed minus 1. As I said, I put the things I've substituted in parentheses so they're easier to pick out. And factor cancel substitute. It'll work. All right, let's clean it up first off. This is just 2h. This is minus h cubed, minus 1. This is minus negative 1, so this is plus 1. I can cancel the 1 and the plus 1, leaving us with 2h minus h cubed over h. Let's factor an h out of the numerator. H times 2 minus h squared over h. There's the factoring. Of course, next we'll cancel the h's and then we'll substitute in. It's factor, cancel, substitute. Okay, here's that last line we had. Cancel the h's next. Can you justify that? Is h non-zero? Yeah, we're taking a limit as h approaches 0 from the positive side. That means a bunch of stuff, among which is h is not 0. So we wrote h is not 0 explicitly. Maybe implicitly, but it's implied by this limit symbol. Can you plug in h equals 0? Yeah, it's a polynomial, and we get out 2. So the right-hand derivative at 0 is 2. Let's check the left-hand derivative at 0. Okay, so we'll take a limit as h approaches 0 from the left, from the negative side. G of 0 plus h minus g of 0 over h. Okay, what's g of 0? When x equals 0, we had this. let's check back on the previous slide. G of 0, you input 0, yeah, you use this piece. You input 0, you use this piece. You input something negative, you use that piece. We input 0, we use the cubing stuff. 0 plus h, what's up with that? Well, h is a little negative number. So 0 plus h is a little negative number. Well, you use this x minus 1 over x plus 1 part of g when you input negative stuff. So what's g of this little negative number? Little negative number minus 1 over little negative number plus 1. It'd be 0 plus h minus 1 over, wherever there's an x, put a 0 plus h plus 1. Stuff in parentheses is where the x's are down here. We're substituting in 0 plus h. Why did you use this piece? Because 0 plus h is negative, and that's the piece you use when you have negative inputs. Clean it up. Okay, so drop the 0 here and here. That'll give us an h minus 1 over h plus 1. Minus a negative 1 produces a plus 1 over here. How about we get a common denominator of h plus 1 over these three quantities? So I'll have to take the first one and multiply by h plus 1 over h plus 1. This already has a denominator of h plus 1. I'll have to take this third one and multiply by h plus 1 over h plus 1. Skipping a step of algebra. If you need to pause this and convince yourself the following is the case, that would be a good idea. So we'll have h times h plus 1 minus 1 plus h plus 1, each divided by h plus 1. I can cancel the h plus 1 and the h plus 1 here on that part to get the 1. I can cancel the h plus 1 and h plus 1 on this part to get the h, and reverse engineer it like that. And you still got the minus 1 over h plus 1 in the middle. Get a common denominator, add them together. This is what we had on the previous slide. Let's clean it up. Or what are we doing? We're trying to factor, ain't we? H times h plus 1, that gives us h squared plus h. When I distribute, the minus 1 is here. H plus 1 is here. Hey, the 1 and the negative 1 cancel. Hey, the h and no, they don't. So I saw something else cancel. The 1 and the negative 1 cancel. So that'll leave us with an h squared plus h plus h. That's an h squared plus 2h in the numerator. Denominator has the h and the h plus 1 in it. Can you plug in h equals 0, by the way? Well, not until after you've canceled. We haven't even factored yet. Can you factor an h out of the numerator? Good thing we got that common denominator. I knew I could factor it if I fiddled with it the right way. So factor an h out of the numerator. Then we can cancel these h's. If h isn't 0, we're taking a limit, leaving us with h plus 2 over h plus 1. Limit as h approaches 0. Can you substitute in? Yeah, it's a rational function, if you like, for justification. And we get out 2. Then we get out 2 from the left-hand derivative as well. Here we're taking a right-hand derivative. They're the same. Left and right-hand derivatives were both 2. So the two-sided limit exists by Theorem 2.6 if you want justification. It does the same thing from the left and the right. So the two-sided limit exists, that is, the derivative exists. And the derivative is that common value of 2. We got 2 from the left, we got 2 from the right. Two-sided, we get 2. And it, this time, the limit, is the derivative of that function. So yeah, it's differentiable, and the derivative is 2 at the point of interest. All right. Hey, what could go wrong if a derivative doesn't exist? Then what's the problem? Well, the book gives 6 cases here. One of them is the following, and we'll see examples of this soon. A corner could occur where the one-sided derivatives are different. On the previous example, the one-sided derivatives were the same, so we were good to go. Here's an example where if we took derivatives from one side, we get the slope of this line. Derivative from the other side, we get the slope of this other line. It's the darkest of these little lines they've drawn here. what they're doing is they're taking, trying to take a derivative at point P. They go to the left, to the negative side. You can see that little symbol there. They've gone to the negative side a little bit and chosen a second point and then slid it along, creating more tangent line, more secant lines, the limit of which will give this particular line here. They've indicated it's sweeping over the movement with these little arrows. And same thing here, we've gone now to the right a little bit, chosen a point and made that point close to point P, and that generates these other secant lines. In the limit, we get this line. Well, they ain't the same because it's got this little sharp point in it. They call that a corner, at least in this edition of the book. And well, you got a problem. The one-sided limits are different in this case. So the two-sided limit doesn't exist. So the derivative doesn't exist. What the graph looks like is it's got like a corner in it, a sharp point in it. Could have a cusp. We've encountered this when we talk vertical asymptotes. We mentioned cusps along the way. What happens here is if we take a limit from one side, we're getting positive infinity out from the derivative. And if we take the limit from the other side, we're getting negative infinity out. If we got positive infinity out from both sides or negative infinity out from both sides, we actually have this case over here, we'd have a vertical tangent. That's what we defined a vertical tangent to be. If left and right limits were both positive infinity or both negative infinity, we had a vertical tangent. If they're both infinite, but one's positive infinity and the other one's negative infinity, you'll have this so-called cusp. It's got this little sharp point in it here as well. In this case, we're getting a limit of positive infinity out. See, these lines have positive slope over here when we come in from the left. When we come in from the right, we're getting negative infinity out. These secant lines have negative slope. If it were the other way around, just imagine taking this picture and turning it upside down. And we'd have a cusp where it comes down to a sharp point and then goes back up. Both of those are examples of cusps, where we get infinite limits, but one side's positive, the other side's negative. We could have vertical tangents, as we've mentioned earlier. The cube root function has a vertical tangent at the origin. The function could simply be discontinuous. If it ain't continuous, then we're going to have some problems talking about slopes of tangent lines, as we'll show in a theorem in just a second. They try to illustrate it here by taking these secant lines and indicating the limit process with the little arrows. Here, from one side, we get a horizontal line. From the other side, we get a vertical line. They ain't the same. So the one-sided derivatives are different. From one side, it's 0. From the other side, it looks like it's positive infinity. They ain't the same. And we've got a problem. Here, we've got a problem as well due to a discontinuity. And I'm a bit hesitant to mention this one. They call it wild oscillation. Yeah, I could have functions that oscillate wildly and they could still be differentiable, and they're not clear on what they mean by wild oscillation. The problem here is they've tried to indicate by all these little lines that come out here and there is if I take tangent lines here, they're going to oscillate between slopes of -1 and +1 in this particular example. And they call that wild oscillation. Okay. They're looking at the function x sine 1 over x. If we were to change that to x squared sine 1 over x, it'd be differentiable at 0, it turns out, with a piecewise definition. So I'm hesitant to get into the wild oscillation. Really, the ones that will affect us is because we'll graph these things, is corners, cusps, and vertical tangents. Now, there's some other things that can go wrong as well. These part 4, where they talk about the discontinuities, that we can explain with Theorem 3.1. This is an extremely important theoretical result. It says differentiability implies continuity. If f has a derivative at x equals c, then f is continuous at x equals c. So differentiable at a point implies continuity at a point. Let's go through proof of that. Maybe make a quick observation that the converse of this doesn't hold. That is, a function can be continuous at a point and not differentiable at the point. The absolute value function is continuous but not differentiable at 0. It's got a sharp point in it. I'm sorry, it's got a corner in it, is how they word it here. Here's a function that's continuous but not differentiable at this point P. Here's a function that's continuous but not differentiable at this point P. Here's a function that's continuous but not differentiable at this point P, for a variety of different reasons. The absolute value function is probably the one most familiar to you, and it's got a sharp point in it. Its graph is a V. And at the origin, it has a sharp point, a corner is what the book calls it. So if we have differentiability, then we have continuity. Let's look at the proof of that. Okay. If f has a derivative at x equals c, then f is continuous at x equals c. By the definition of continuity, we need to show the limit as x approaches c of f of x equals f of c. We broke continuity into 3 pieces. We needed the function to exist, we needed the limit to exist, and we needed the limit to be the function value. In a synopsis, the test for continuity boils down to establishing this. We've mentioned this in the past when I think we did exercise 2.5.72 in the supplements. But at that point, we used exercise 71 that says, equivalent to showing this, we can show the limit as h approaches 0 of f of c plus h equals f of c. So if we can show that, according to exercise 2.5.71, that's equivalent to showing continuity. I like this because I've heard of this c plus h stuff before, or at least x plus h. All right, so let's take a limit as h approaches 0 of f of c plus h. All right, looks like it equals f of c and it's going to work. Let's take f of c plus h and write it like this. I claim this equals f of c plus h. So look what we got here. You could cancel the h's, provided h isn't 0, it isn't, we're taking a limit. Then we'd have a minus f of c over here. We got an f of c over here. We can cancel those. We'd just be left with this f of c plus h. Indeed, the stuff in parentheses does equal f of c plus h. So the limit as h approaches 0 of f of c plus h is the same as the limit as h approaches 0 of this stuff here, because this stuff here equals f of c plus h. Why would you want to write f of c plus h like this? Well, this part ought to catch your eye. There's a difference quotient. And what do you know? We know the derivative of f exists at x equals c. So I'm trying to get into this somehow or other, the definition of derivative. So you can't argue with the validity of this. It's just algebra. The limit of the sum is the sum of the limits. So we could write this as the limit of this plus the limit of that. That's a product. The limit of the product is the product of the limits. All of this under the blanket assumption that the constituent summons and pieces of the product, those limits exist. They do in this case, and that's where we use the hypothesis of the derivative exists. So limit of the sum is sum of the limits, limit of the product is the product of the limits, assuming those constituent pieces exist as limits. Does the limit as h approaches 0 of f of c, does that exist? Yeah, that's a constant, that's just f of c. How about the limit as h approaches 0 of f of c plus h minus f of c over h? That's from section 3.1. That's the derivative of f evaluated at c. By definition, that's f prime of c. You sure that exists? I am. F has a derivative at x equals c, and that's what it is, commonly denoted f prime of c. So right there's where we use the hypothesis that the function is differentiable at c. Limit as h approaches 0, which of course that's just 0. So we've got f of c plus f prime of c times 0. That's f of c. Limit as h approaches 0 of f of c plus h equals f of c. Exercise 2.5.71, that function's continuous at c. So differentiable implies continuous. Converse doesn't hold. We saw a bunch of examples of that just a second ago. The standard example is the absolute value function, but we had some others in terms of the pictures there. Now, it gets a lot worse than that. The homework exercises 3.2, the section we're in, number 64, mentions that there's a continuous function that isn't differentiable anywhere. This is pretty exotic stuff. I'm surprised they even mention it in a calculus course. They give you this function as, this is called a series. It's a sum. You might be familiar with the summation notation, maybe from statistics. Sum from n equals 0 to infinity. So it's an infinite sum. Such a thing's called a series. You'll explore series in calculus 2. It's, I don't know, probably chapter 8 or 9 of the book. But anyhow, there exists this function that's continuous everywhere, but it's not differentiable anywhere. It's continuous, but nowhere differentiable. The absolute value function, it's continuous and not differentiable just at 0. This thing's continuous, but not differentiable anywhere. So it's a pretty wild, exotic function. This is a result due to the creation of this function, the establishing of the properties of this function. It's called, we give it a name, the Weierstrass function. Yeah, the Weierstrass function is defined here, and never mind, this is way beyond us to establish the validity of this in Calculus 1. It's a bit of a thing to establish in an analysis class. But it's named after Carl Wilhelm Weierstrass. His dates, kind of the early part of the 19th century to almost 1900. Did his work in the late 1800s, last half of the 19th century, sometimes called the father of modern analysis. The research he did relates to our senior level analysis classes, analysis 1 and 2. This is a class where you would take all this calculus stuff and put it on a sound, rigorous foundation. You define the real numbers as a complete ordered field. And we've done that. If you've looked at the appendices, it's done in Appendix A6 of the current edition of the book. And we'd go through with this epsilon delta stuff that we mentioned earlier and just go nuts with that kind of thing. Weierstrass was fundamental in the foundations of some of this rigorous analysis stuff. It's Cauchy that brings you the epsilons and deltas. There's plenty of other names in the history of analysis. Weierstrass is really most influential as a math instructor at the University of Berlin. Here's his years of operation. And in his lectures, he laid out cleanly and rigorously a lot of the properties of calculus and put them on a rigorous foundation. He taught classes in an introduction to analysis. We've got a class in that. Integral calculus, you know, that's mostly what calculus 2 is, about the first half of calculus 2. General theory of analytic functions, that relates to the series stuff. You'll touch on these ideas in calculus 2. In fact, this idea of an analytic function, a function with a series representation. And something called calculus of variations. This calculus stuff's pretty useful. ETSU doesn't have a calculus of variations class, but it deals with optimization. Let's leave it at that. It deals with optimization for some difficult problems. Can you prove the shortest distance between 2 points is a straight line? Prove it. You can with the calculus of variations. We do have a class, differential geometry, where we prove that and touch on some ideas from calculus of variations. But it's an optimization process, this calculus of variations. And we'll do a good deal of optimization in chapter, I think in chapter 4, we'll do max-min problems. It's 1872. Here's that austere chap, Weierstrass, 1872, that he comes up with this idea of a continuous nowhere differentiable function. This super quick biography brought to you by Wikipedia. What you read on Wikipedia, take with a grain of salt. And the Mac Tutor History of Mathematics Archive, I've mentioned that before, a very reputable website with more math history than anybody could possibly want to know. So there's just some references on that. That image, by the way, is from the Mac Tutor site as well. Let's do a couple more examples and that'll get us through this section 3.2. Okay, they give us a graph here and they say, consider the function graphed with domain -3 to 3. At what domain points does the function appear to be, part A, differentiable, Part B, continuous but not differentiable. Part C, neither continuous nor differentiable. Here's the graph. Starts here. Yeah, I can draw without picking up my pencil. That sounds awfully continuity-ish to me. So it is continuous. Let's explain it away somewhat informally. Let's see, what are we talking about? Differentiable, we're going to address first. It looks like it's differentiable at -3 from the right, at +3 from the left. If you think about tangent lines, I can make sense out of tangent lines when we take one-sided limits as h approaches 0 as appropriate at the endpoints. So it does have, and this is a light explanation, I'm saying look at the picture, and that's the intent of the question. They didn't give us a formula, so we can't really check it otherwise. But it looks like it has nice left and right hand derivatives as appropriate at the endpoints. The graph is, using the word smooth, this will actually take on a meaning probably early in calculus too. It's a little more complicated than I'm using it in the current context, so I'll put it in quotes. But just between you and me, it looks like a nice smooth curve, except where it's got these two corners. And where it's got those two corners, we've made a claim that that's a problem for the derivative. Yeah, and we could take left and right hand derivatives at, looks like -2 and at +2. And the left and right hand derivatives would be different. It's got a corner, as the book calls it, at these 2 points. And it's not differentiable at 2 or -2 because of the corners, the sharp points. Everywhere else, we wouldn't have any problems with it being a nice smooth function, and the derivative would exist. And we could talk about tangent lines at all those other points between -3 and 3, except for 2 and -2. And I got to be careful how I deal with the endpoints with the left hand and right hand derivatives. So where's it differentiable? On the interval from -3 to 3, except at -2 and 2. So I'll throw out -2, I'll throw out 2, and write it as a union. So we've got differentiable on that interval, on its domain, except at 2 and -2, with the appropriate meaning of differentiable at the endpoints of that interval. Part B, what's up with continuity, but not differentiable? It's continuous everywhere, we decided. Maybe take Dr. Bob's anthropomorphic idea of continuity. You want to think about it as not picking up your pencil, yet that'll work since it's defined on an interval. There's some places where that won't work, places where anthropomorphic stuff won't work either. But on this interval, we're okay. That's certainly a continuous function. So it's continuous on the interval from -3 to 3 throughout its domain. It is continuous with the appropriate meaning of continuity at the endpoints, but we had problems of differentiability at -2 and 2. So the question was, where it is it continuous but not differentiable? The answer is at +2 and at -2. And at part 3, they wanted to know where it was neither continuous nor differentiable. Well, it was continuous throughout the interval, so there's no points such as that in this one. These were the instructions for a set of several graphs. For this one, there's the solution. Okay, one last one from this section. Does any tangent line to the curve y equals the square root of x cross the x-axis at x equals -1? If so, find an equation for the line and the point of tangency. If not, why not? All right, y equals the square root of x. We've dealt with that function several times. We've dealt with a graph of it not so long ago. It's half of a parabola, opening rightward in the first quadrant of the Cartesian plane. And they want to know, does a tangent line of this curve cross the x-axis at x equals -1? In your mind, you could draw a picture, or we can plow into the algebra. Well, a line with slope m, which crosses the x-axis at -1, that means it's got an x-intercept of -1, would be of the form y equals m times x minus x sub 1, slope-intercept form of a line. Here, we want the intercept to be -1, so this leads us to a line of the form y equals m times x plus 1. If it has a tangent line, that crosses the x-axis at -1, it has x-intercept of -1, then it's of the form y equals m times x plus 1. How are you going to find m? How are you going to find a slope around here? Well, they wanted it to be tangent to this curve. Slopes of tangents to a curve are given by derivatives. So we need a derivative. All right, so first we'll set it up. We're looking for a line of the form y equals m times x plus 1. I don't know what m is. Well, let's find the derivative of the square root function. Starting in the next section, we'll streamline this and won't have to go through quite so much limit stuff once we establish rules of differentiation, which we'll establish using limits. So f of x equals square root of x. Then f prime of x is the limit of h approaches 0 of f of x plus h minus f of x over h. Get that in your head because it's fundamental. In this case, we're dealing with a square root function, so f of x plus h is the square root of x plus h. F of x is the square root of x. We divide by h. When you have these square root things, you should be used to, by now, evaluating limits by multiplying by the conjugate over itself. Do that. Distribute. Okay, that'll give us the first squared minus the second squared. That's the reason we multiply by the conjugate. Got a difference here, put a sum over here. Denominator gets a little bit messy, but we'll take care of it. Square root of x plus h squared is x plus h. Square root of x squared is x. We've lost some information that none of this stuff can be negative. Right? They were x values from the domain of the function. So implicit in this somewhere is that x isn't negative, and we still got that information in the denominator, by the way. The x's cancel. That leaves us with a limit as h approaches 0 of h divided by h times this other stuff. So we got it factored, and it factored easily because everything disappeared with the h itself in the numerator. Now we can cancel the h's. As long as h isn't 0, it isn't, taking a limit. That leaves us with this. We can substitute in y. No square roots and negatives. And we're taking square roots. So that's what I'd worry about, is square roots and negatives. There are none. I can justify that in much more detail. I trust you're sick of that by now, about the fact that x plus 0 must be non-negative for the appropriate x values, blah, blah, blah. And that's 1 over 2 on the square root of x. So the derivative is 1 over 2 on the square root of x, and that'll represent slopes of tangent lines. So I'm going to relate this derivative to that slope m. Now, I don't know what that slope m is. All right. Slope of the function, say at a point x sub 0, x equals x sub 0 would be f prime of x sub 0 would be 1 over 2 square root of x sub 0. Just plug x sub 0 into what we had on the previous page. So we need to find x sub 0 such that the line y equals m x plus 1 has this slope. I know the slope, if it's tangent to the curve, will be of this form. This slope times x plus 1. And we need this to contain a point on the curve y equals square root of x. When we plug in x sub 0, what do you get out of this function? Square root of x sub 0. So we need y equal 1 over 2 on the square root of x sub 0, x plus 1. And we need this to contain the point x sub 0, square root of x sub 0. It's a point on the curve, and it's a point on the tangent line. The point of tangency to the curve. All right. So we need this point, x sub 0, square root of x sub 0, to equal what we get here by plugging in x sub 0. Call it x sub 0, y sub 0 if you like. X sub 0, I don't know what it is, but I know what y is in terms of x sub 0. Here I've used the function information. Here we've used the line information. So when I plug x sub 0 in for x here, that gives a corresponding y coordinate. I need that point on the curve to equal this point on the line. Well, our x coordinates are the same. We made it that way. We need their y coordinates to be the same. That's how we'll find x sub 0, if such an x sub 0 exists. If this equation we're about to set up has no solution, then there is no such point and such line. Okay, so we need these 2 points to be the same. So look at the y coordinates. We need the square root of x sub 0 to equal this stuff here. We need the square root of 0, square root of x sub 0 to equal this stuff here. So solve this for x sub 0. All right, only one unknown. We got the square root stuff, kind of bugs me. Let's cross multiply. Let's take the 2 square root of x sub 0 to the left-hand side. That'll give you 2 times the square root of x sub 0 times the square root of x sub 0. That'll get rid of the square root. And on the right-hand side, you'll just be left with the x sub 0 plus 1. Cross multiply, 2 square root of x sub 0 squared equals x sub 0. That's 2x sub 0 equals x sub 0. Yeah, remember x sub 0 better be greater than or equal to 0 because it's in the domain of the square root function. If we get something negative out, then we're in trouble. We won't. Let's see, subtract x sub 0 from both sides, and that'll leave you with x sub 0 equals 1, which is big time positive, so we're okay. So when x sub 0 equals 1, we can figure out what y sub 0 is. Plug in maybe here. We'll have a 1 in the denominator, gives a 1/2 times 1 plus 1. Let's give us 2 over 2. Yeah, give us y sub 0 equals 1. So that point is 1, 1. How about the slope? I got it written, m equals somewhere. Here's a slope right here. It's 1 over 2 square root of x sub 0. X sub 0 equals 1. That slope must be 1 over 2 square root of 1. Must be 1/2. So the point is 1, 1. The slope is 1/2. The equation of the line we can figure out now because we just figured out what m is. So yes, there is such a line. It's the line y equals m, or m is 1/2, x plus 1. We already knew that from how we started the problem. And the point of tangency is the point we've labeled x sub 0, y 0. X sub 0 is 1, y sub 0 is 1. And there you go. So there's how to algebraically deal with a question of this sort. If it talks tangent lines, it's got to be related to derivatives. It could have been that there is no such line. It depends on the curve. Different curve might not have such a tangent line. We'd go through and analyze it in a similar way. And something would go wrong probably at the end. And we'd see we get a system, an equation involving, say, x sub 0 that has no solution, x sub 0. So process would be the same even if no solution existed. And that takes care of, doesn't it? Yeah, that takes care of section 3.2. In the next section, it's rules of derivatives. If you've seen derivatives before and you've taken derivatives the easy way, we're about to introduce that stuff. But it has to be established, and it'll be established using all this limit as h approaches 0 stuff, all this definition of derivative stuff. But once we get that, this taking of derivatives will become even more mechanical, become more easy too. I will see you in section 2.3. Have a nice day.